Now we are ready to prove the division algorithm for polynomials, and we are going to prove this for polynomials of rational numbers, but the same argument is also applicable to polynomials of real numbers or complex numbers. Anyway, here's the theorem, that is division algorithm. Division algorithm. So let a of x and b of x be polynomials of rational numbers, and we assume b of x is non-zero. Then there exist polynomials q of x and r of x in this set such that a of x is equal to b of x times q of x plus r of x, and either r of x is 0, or if it's non-zero, then the degree of r of x is less than the degree of b of x. Okay. So this division algorithm for polynomials is very similar to the division algorithm for integers. The main difference is that since we are not dealing with numbers and polynomials are not linearly ordered, we do not compare the magnitude of R polynomials. I mean, we cannot measure the magnitude of polynomials other than the degree. Okay, so instead of comparing the modulus of remainder and the divisor, we compare the degrees of these polynomials. So when r of x is 0, then that means b of x is a divisor of a of x. Otherwise, the degree of r of x, which is greater than 0, not exactly greater than 0. It can be greater than or equal to 0 because it can be a non-zero constant, but the degree is less than the degree of b of x, this one. By the way, the notion of degree is undefined for zero polynomials, so that's why we need a separate mention here. Anyway, let's prove this theorem. Suppose we have these polynomials a0, a1, x, and so on, and the degree is n. So that means this coefficient is non-zero, and b of x and bn x to the power of n, and bn is not equal to 0. And first we consider the trivial case. So if the degree of a of x is less than the degree of b of x, then we have a of x is equal to 0. Wait a minute. b of x times 0 plus a of x. So this expression satisfies this form, right? So in this case, q is 0 and r of x is a of x, and the degree of a of x is less than b of x by assumption. So that is okay. And then if the degree of a of x is 0, then a of x is something like a 0. And if degree of a of x is equal to the degree of b of x, then that means b of x is also a constant. By the way, this shouldn't be 0 because we're assuming that this polynomial b of x is non-zero. So in this case, we can express a of x as b of x times a0 over b0. As we've mentioned, b0 is non-zero, so we can divide by b0, so no problem. So in this case, we have this trivial divisor, and we can express a of x as in this form. The remainder is 0. Now, consider the case where if the degree of a of x is greater than 0. And we use induction. So as an induction hypothesis, suppose that the result is true for all polynomials of degrees strictly less than degree of a of x. Okay, here the result means we can express some polynomial in terms of b of x times some polynomial plus the remainder. Okay, so suppose we have this form for all polynomials that have degrees less than the degree of a of x. Okay, and if the degree of a is less than the degree of b, we have already proved here. So we may assume the degree of a of x is greater than or equal to the degree of b. Okay, now we define a new polynomial f of x by a of x minus am over bn times x to the power of m minus n times b of x. And we assume the convention that x to the power of 0 is 1. Okay? So this means so the degree of b of x is n, and the degree of a of x is m. So if we multiply this term, x to the power of m minus n, then the degree of the polynomial, this term times this is the degree will be the degree of this term, this whole term is equal to m, right? And the coefficient of that polynomial is multiplied by am and divided by bn. So the coefficient of the term of x to the power of m is equal to am, and that is subtracted from a of x. So that means the degree of f of x is now less than the degree of a of x, because by this operation, by subtracting this polynomial, the highest order term is cancelled. So there is no term with x to the power of m, but all the powers are less than m. That's why we have this inequality about the degrees. So by the induction hypothesis, we have this expression. So f of x can be expressed as b of x times p of x plus r of x for some polynomials p of x and r of x. And of course, r of x can be either 0 or its degree is less than the degree of b of x. It's part of the induction hypothesis. Now, let's substitute the definition of f of x into this equation. Then this means we have a of x minus am of bn times x to the power of m minus n times b of x. And p of x, r of x. Now we move this term to the right hand side. Then we have a of x and factorized by b of x. And we have this and am of bn x to the power of m minus n and plus r of x. And so the degree of r of x is either 0 or its degree is less than the degree of b of x. And this is another polynomial, so we could set this as q of x. So this satisfies the form that is claimed in this theorem, and we are done. The next theorem is called the remainder theorem. Okay, that says suppose we have a polynomial and a rational number c, and first there exists some polynomial q of x such that f of x is equal to x minus c times q of x plus f of c. And second, x minus c divides f of x if and only if f of c is equal to 0. Now this second part is trivial from the first part. So let's prove the first part. Okay. By the division algorithm, we have just proved division. There exists some polynomials q of x and r of x such that f of x is equal to x minus c. Of course, x minus c is a polynomial, so we can apply the division algorithm. And r of x, where r of x is either 0 or if r of x is non-zero, then the degree of r of x is less than the degree of this x minus c, which is 1. So this means r of x is a constant. Let's call it r0. So this is either 0 or non-zero. So in either case, we can express r of x as in this form. So it's a constant, whether it's 0 or not. But if we substitute x with c, then we have c minus c times q of x plus r0. But this part is 0. So r0 is equal to f of c. So we replace r of x with f of c, then we have the desired equation. And we are done. And from this, the second part should be trivial. Let's see an example of how to apply this theorem. So, example, and suppose we have a polynomial 2x to the power of 5, x to the power of 4, 7x to the power of 3, 2x plus 10. Now, this is divisible by x plus 1. Why? Because if we substitute so this means this polynomial can be expressed as x plus 1 times some polynomial plus 0. So we just ignore this part. So to see this, we just substitute x with negative 1. Okay, so if we calculate this, so 2, negative 1, and negative 1, negative 1, negative 1. So that is negative 2 plus 1, negative 7, negative 2 plus 10. So that is indeed 0. So according to the theorem, so f of c is 0. So that means in this case c is negative 1. So x plus 1 divides this polynomial. Now, based on the division algorithm for polynomials, we can develop the Euclidean algorithm to find the greatest common divisor of two polynomials. And let's illustrate this by an example. Suppose we have two polynomials, a of x, that's 2x cubed minus 5x squared minus 2x minus 3, b of x x cubed minus x squared minus x minus 15. So first divide a by b. So that's 2x cubed minus 5x squared minus 2x minus 3 equals, so if you divide this by applying the division algorithm, the result will be this. This is 15. Okay. And the remainder is minus 3x squared plus 27. You should verify this by using, for example, just expanding this or by long division. Now, okay, this part is A and this part is B and this part is the remainder. Next, we divide this one, B, by the remainder. So that is x cubed minus x squared minus x minus 15. So divide by this, minus 3x squared plus 27, and the quotient part is 1 over 3 times x plus 1 over 3, and the remainder in this case should be 8x minus 24. Again, you can verify this by expanding everything here. Now, next we divide this part by the remainder. Okay, so that is negative 3x squared plus 27, 8 minus 24 times negative 1 over 8x minus 9 over 8 with no remainder. So at this point, by using the analogy between polynomials and integers, we guess that this polynomial should be the greatest common divisor. But please recall the definition of the greatest common divisor for polynomials. If it is a greatest, for a polynomial to be a greatest common divisor of some other two polynomials, then it should be monic. That means the coefficient of the highest degree term should be 1. So this is almost the greatest common divisor, but we need to make the coefficient, in this case, coefficient of x should be 1. So 8x minus 24. So we factor out 8. So that will be 8 times x minus 3. So this one, x minus 3, is the greatest common divisor of a of x and b of x. And furthermore, let's see, following this process of division algorithm backwards, so starting from here and going backwards, we can find this 8x minus 24 is equal to, so move this term to the left hand side, and we have x cubed minus x squared minus x minus 15 minus so minus 3x squared plus 27 times negative 1 over 3 times x plus 1 over 3. And this one is b of x. And let's see, b of x, and this one is, let's see, so that one was obtained from this, so it's a remainder here. So this is equal to this part minus this part. Okay, and let's change. So this is a of x, and this part is b of x. So this polynomial is a of x minus 2 times b of x. Okay, so this is a of x minus 2 times b of x times negative 1/3 x plus 1/3. And so let's expand this. We have a of x, so this times this. And this times this plus this, so that is b of x times negative 2/3 x plus 5 over 3. So that's what we have here in the end. So this is analogous to the integer case. So in the case of integers, if d is a common divisor of a and b, integers a and b, we have something like this. And a, b, d are integers, and x and y are also integers. And d is the greatest common divisor of a and b. So just like integers, we have a similar expression for polynomials. In the case of polynomials, we have some constant multiple of the greatest common divisor is equal to one of the polynomials times some polynomial and the other polynomial and some other polynomial. So this a corresponds to this b corresponds to this x corresponds to this polynomial, this y corresponds to this polynomial in this case. And of course we can prove the Euclidean algorithm for general polynomials, but it's a little bit tedious, so I would just skip it.